Hi, my name is Amy Zhang. I'm an emerging data analyst, just wrapping up CareerFoundry's excellent program. And today I'd like to share with you my final portfolio project. Hidden Currents, an investigation into water usage reporting in US power plants. So when I started out this study, I already knew how much water matters. It's the only substance that every single living system depends on, including the ones we build. Cities, my favorite built typology, rise and fall with the quality of their water management. Rome wasn't built in a day, and it certainly couldn't have been built without its aqueducts. We use energy to treat, heat, and move water, and we also use water to produce energy, hence the water-energy nexus, the Watergy nexus. The rise of AI and data centers has certainly made this relationship more visible. Water acts as a coolant to keep electrical systems running, and when we can't maintain a sufficient temperature difference with the environment, electricity production actually becomes a lot less efficient. As global temperatures rise, that's becoming much harder to do. In short, we're starting to need more water precisely when we have less of it, both consistently and equitably. So yes, I already knew that water mattered. What I didn't know, or rather didn't fully expect, was how hard it would be to properly scope this project. By my third failed dataset merge and 70-column reverse engineer, I started feeling like Medusa's hairdresser. Every attempt to trim the frame turned into another stone-cold dead end. Eventually, I narrowed my focus to the Energy Information Administration's thermoelectric cooling data, 9 years worth from 2015 to 2023. And my refined goal became this: what patterns in data quality could inform lightweight, real-time anomaly detection models to support better water usage reporting? Here are a few of the things that I found. Insight number 1, missingness is structural. Missing data is not random. It clusters around key attributes like plant size, fuel type, and cooling technology. So in this heat map, I ranked power plants defined by plant type and fuel source across 4 different dimensions. 1, the total number of plants, 2, the total number of missing rows, and 3, average missing per category, and 4, average missing per plant. So the rate of missingness for the average individual plant in that category. Unsurprisingly, large thermal combustion plants, your classic coal and fossil fuel setups, top the charts in raw missingness, but this is partly because they're the most common historically. Once you normalize, medium thermal combustion plants start to look more suspicious on a per plant basis. That might reflect greater variability in how they're configured, or maybe they just fly a little further under the audit radar than their larger, more centralized counterparts. And then there's a twist. Non-steam and large non-combustion plants, which are likely nuclear, they show lower but still notable levels of missingness. What's more surprising is how often fossil fuels show up in their reported fuel types. That speaks to the complexity of mixed generation plants, where solar, nuclear, and fossil fuel systems might all coexist. And when that happens, cooling system reporting gets messy very fast, a little bit like hair that gets stuck in the hinge of glasses. So, thank you. Insight 2, missingness is not the only issue. There are anomalies beyond absence. So some early statistical summaries revealed something even stranger than missingness. Certain plants were reporting negative water values. At the time, I barely knew a cooling tower from a transformer, but even I knew that negative water values were physically impossible. They suggest that water was somehow produced during energy generation. For most of the plants, these errors disappeared once I aggregated from monthly to yearly data, but for 4 plants, the negatives persisted. Zooming in on these outlier plants revealed even more anomaly types beyond absence. So first, there were implausible 1-to-1 ratios. These are plants where the water withdrawal volume and consumption volume were reported as exactly the same month after month. This results in these line graphs that mirror each other too perfectly. It's either an improbable coincidence or a reporting shortcut. It suggests that all the water taken in was lost, or worse and weirder, given the negative water metrics, that water somehow multiplied itself. I guess that would actually be kind of wonderful. But you see how quickly this breaks down. There's also phantom reporting, sparse, disconnected clusters of entries from plants marked as inactive, but still submitting data. These ghost plants distort missingness statistics and trend analyses. And then you have extreme spikes, or negative and positive in the data set. But this one here is negative, a single massive negative outlier, which is totally out of scale with its surrounding data. Establishing meaningful outlier thresholds will certainly require further analysis by plant type and cooling tech. As we saw in insight number 1, missingness clusters by certain attributes. And it's likely that standard water use behaviors are even more sensitive to these different subsets or subcategorizations of plants. Together, these red flags became the foundation for an incremental suspicion score, a metric assigned to each plant month record through the addition or subtraction of points based on the presence of the anomaly conditions. Insight 3, suspicion score profiling. So if Insight 2 showed us that anomalies go beyond simple absence, Insight 3 asks, how do we start predicting where those anomalies are likely to show up? So with the suspicion score calculated, I can now look at how they were distributed across plants by these various features like type, fuel source, cooling system, and configuration. By normalizing scores within each category and then measuring their variance, I used standard deviation as a proxy for how predictive a feature might be. My thinking was that higher standard deviation or higher volatility could also mean the data itself was more sensitive based on fluctuations in that particular feature. That feature, in other words, might be helping us surface risk. It's a little ad hoc, and in just a minute, I'll address other options. This chart shows features ranked from most to least predictive alongside the most anomalous category for each. And the results are sometimes expected, but often surprising. So plant type came out on top, but the most anomalous group was large non-combustion plants, likely nuclear, or usually referring to nuclear plants. That's surprising given their relatively mild missingness in Insight 1, certainly compared to the large thermal combustion plants, the fossil fuel plants. My current hypothesis is that it's the combustion-based secondary generators that are flying under the radar of these top-line classifications. We got a glimpse of this in Insight 1, so I'm talking about those unexpected fuel pairings like large non-combustion with natural gas or non-steam, which one usually uses to refer to renewables, but paired with coal. These odd combinations hint at the multi-generator setups behind the scenes, and that's essentially my best guess for where these suspicious patterns are surfacing. Next, you have prime mover and fuel type. And their top value is for solar-related categories, which is a bit odd since solar typically uses very little water. That could suggest classification drift or reporting inconsistencies, certainly worth investigating as we expand renewable infrastructure. Cooling design flagged dry and hybrid systems as highly volatile. These are technologies often used in water-scarce regions, and so it makes it especially critical to understand where the accounting might be breaking down. And lastly, configuration types like MC1G, 1B, meaning multiple cooler linked to one generator, linked to one boiler, and that's the setup for the cooling system. Also generation technology like combined cycle single shaft, and combined heat and power, these all showed high risk. All these tend to be more decentralized or custom engineered setups, and so this might open the door to edge case behavior and greater reporting inconsistency. Together, these patterns start to reveal which features could help predict future data issues and inform better quality controls or early warning anomaly detection tools. Before wrapping up with recommendations, I'll quickly share 2 mini experiments that emerged organically during the project, each suggesting directions for deeper development. The first is sector forecasting. I initially attempted to forecast water usage by sector with a special interest in detecting the growing footprint of data centers. But that proved quite tricky. Without NAICS codes, data centers are very hard to isolate in the records. While some sectors, such as utilities, show clear seasonality in their withdrawal patterns, others display extreme volatility. For long-term sector-level water assessments, the U.S. Geological Survey actually turns out to be the more authoritative source compared to EIA data. The second experiment, K-means clustering for outlier behavior. Here, I stepped away from my beloved interpretable suspicion score and entered the black box, applying K-means to 2023 plant data. Clustering by net generation, megawatt hours, and water withdrawal, measured in million gallons. The results were promising for exploratory analysis. So cluster 1 cleanly isolates the obvious extremes, but more intriguingly and helpfully, cluster 1 shares a fuzzy boundary with cluster 3, flagging borderline behaviors that I certainly wouldn't have been able to pick out by eye. And these might signal a subtle pattern of irregularities. The key reflection here is that K-means works very well, not as a final model, but as a thinking tool. It shows regions of high suspicion that I hadn't seen with my rule-based logic. A natural next step will be to compare these machine-discovered clusters with the manually defined suspicion scores. Seeing where they align or diverge could help validate and refine both methods. So, for my final recommendations, the first would be to formalize the suspicion score. We could use it to label a training set and to test whether a classifier can learn to predict anomaly risk, validating whether it's capturing meaningful structure. Second, validate with USGS, the US Geological Survey. Cross-reference highly suspicious EIA plants against the USGS water data to check reporting accuracy and to refine the suspicion score. And number 3, cluster and investigate. So use the weighted suspicion score to explore unsupervised cluster trends and definitely take a closer look at 2019. It's an unusual year when looking at consumption by sector and also by month. And that's a wrap on hidden currents. Behind the scenes at the sites powering our lives, I found signs of both innovation and inertia. Along the way, I gained new techniques, just a few new domain-specific terms, and a clearer view of the challenges ahead, from broadening our perspective on water stewardship, even beyond my focus here on optimizing power plant water usage, to breaking down information silos. I am more than ready to dive in.